Well, we're going back into our motivation. Way back on day one, we had this picture. And we said, look, we can find tangent lines. And how do we find tangent lines? Well, we find tangent lines, so the tangent line is this red line, which is tangent. Now, if the word tangent means to touch, so it's just touching the curve at a single point. And we can say, well, the problem is you only have one point to work with, this point on the curve. But secant lines, and with secant you cross, you've gotten 2 points to work with. So secant line, you have an A and a B, and you draw a line. And the moral, the philosophy is, if we let the 2 points get closer and closer, so you have this notion that B is getting closer to A, then the secant lines, which might not be very good approximations if our 2 points are far away, become good approximations as you get close, and become great approximations as you get even closer. And so we have the following. If we now say, using our wonderful terminology, this toolbox that we have, this idea of B is getting close to A, is just another way of saying we're taking a limiting process. There's a limit involved. So limits are, I'm trying to get close to something. So B is trying to get close to A. And now we are trying to find our tangent line. Well, how do you find the line? You need two pieces of information. You need the point, and that's a freebie. So the point of our tangent line, which is this point up here, is always going to be A comma f of A. And now we need something that's going to give us our slope. So this f prime of A, this is sometimes called our instantaneous rate of change. This is the slope of our tangent line. So the derivative tells us how our tangent line is changing. Now remember that we said slopes correspond to rates of change. And so when we had a secant line crossing through 2 points, that was an average rate of change. So it's the change in the output, f of b minus f of a, over the change in the input, b minus a. And now as we take this limit, we get the slope of the tangent line. That's the instantaneous rate of change, how the function is behaving at that point. All right. Well, what do we have? A lot of the things are what we just said. So again, this f prime of a, it's our instantaneous rate of change. It has a couple of different interpretations. So you might see things like find the instantaneous rate of change, or you might see find the derivative. That's the same thing. You might say what's happening at that point. That's again what you're trying to capture is we're trying to express the same thing in many different ways. So understand, what is f prime of a? Well, we call it the derivative of f of x at x equals a. It's how fast the function is changing at x equals a. It's our slope of our tangent line. So we have all these wonderful things. Now there's a different variation that we oftentimes use for our definition of derivative. And this says, okay, let's think of b not as a number, but let's think of b as we took a and then we perturbed it a little bit. So in other words, b is a plus a small change. So what we're thinking of here is we're thinking of this small gap as being h. So to get from a to b, you went h. So now I can say, okay, what changes to the formula? Well, f of b minus f of a, that's f of a plus h minus f of a. And then the b minus a, that's our change, that's h. And so we can write it as f of a plus h minus f of a all over h. Now, I will say that they are both equivalent in that you'll get the same answer. In terms of practical application, when you actually have to apply the definition, and we will get to the point where we don't apply the definition anymore. It'll be about a week from now when we don't have to go back to the limit definition. In practical application, this second one is easier to apply. And the reason I say it's easier to apply is think of the philosophy we had when we were trying to deal with limits. More or less, when we dealt with a challenging limit, which required more work. So something of the form 0 over 0. And then what we wanted to do is we wanted to somehow rewrite the expression so that we got a cancellation of zeros. And so you'll see we do get 0 over 0. Because if you put in h equals 0, you get f of a minus f of a on top. And if you put in h equals 0, you get 0 on the bottom. So this is 0 over 0. So we are in that more work setting. So we want to get cancellation. The reason why it's easier when we just have an h downstairs is now the goal is how do we get an h out of this f of a plus h minus f of a? It's a little bit easier to figure that out. Whereas here, we have to say, okay, to get the cancellation, I need to figure out where's my b minus a. That's a little bit harder to extract. So if you're going to use the limit definition, you can use either, but I strongly encourage you to use this one. All right. So let's do an example. For the quadratic function, f of x equals something, find f prime of a for any a. So we haven't actually written down the quadratic. That's a second order polynomial. So does anyone have a favorite quadratic they'd like us to do? 5x squared. We need a quadratic, so we need a square. We can have more stuff. Plus 7x and plus 2. 5x squared plus 7x plus 2. So I want to find f prime of a for any a. So let's see what happens. So we have the formula that we just had. So f prime of a, that's the limit h goes to 0 of f of a plus h minus f of a, all of that divided by h. Now we run into one of the biggest challenges when it comes to taking derivatives. And we should take a second here and pause to just make sure we understand what's going on. So here's our original function. F of x equals 5x squared plus 7x plus 2. Let's just do a couple of things. What is f of 1? Well, 5 times 1 squared plus 7 times 1 plus 2. That's what f of 1 is. You plug it in. And then you say, okay, after you plug it in, you can do algebra, you can do arithmetic, you can simplify. So you'd get down to 14. What if I plugged in, say, something exotic like negative 2? All right. Well, 5 times negative 2 squared plus 7 times negative 2 plus 2. Okay. So far, all right. You're probably thinking easy, easy. All right. Let's try something a little bit more interesting. Suppose I plugged in f of a cat. What would you get? 5 times your cat squared plus 7 times your cat plus 2. Now you might be saying, but that's nonsense. Yes, it is. But that's the rule. We follow the rule. So whatever the rule is, we make sure we follow it. All right. So as another example, if I just plugged in, say, a, what would I get out? 5a squared plus 7a plus 2. So here's the point. What do you get when you plug in f of a plus h? What do you do? 5 times a plus h squared plus 7 times a plus h plus 2. A lot of people will say, oh, f of a plus h. They're like, well, that's easy, right? Isn't it the case that if I want f of a plus h, that's just f of a plus h? No, it's not. Be careful. So make sure you follow the rule. So once you have a function, whenever you're putting in your a plus h, just everywhere where there was an x before, it becomes an a plus h. So this is our limit as h goes to 0. 5 times a plus h squared plus 7 times a plus h plus 2. And I'm going to use parentheses because parentheses help save points because it helps us avoid mistakes. Now, what I mean by that is whenever you have a minus, you run into a danger of forgetting that a minus distributes through. So, when in doubt, put parentheses and just be careful. So I replace what f of a plus h is, I replace what f of a is. What happens next? Okay, so start doing algebra. What are some algebra things we can do to this? We can distribute, we can expand, we can start gathering like terms. So there should be no real surprises. This is a type of a problem where you just sort of carefully follow through. So a plus h squared would be a squared, so that'll give 5a squared. 2 times a times h, then there's another 5, so that would be 10 times a times h, and then h squared. So 5h squared. That's the first term. Next term, 7a plus 7h. Make sure you get that 7 distributing through. Then you have a plus 2. Then over here, the minus distributes through. Minus 5a squared, minus 7a, minus 2. All over h. Now, if we're good people, what should happen? Things should cancel. And if they're not canceling, you should be very suspicious. You should go back and check your work. In our case, an awful lot cancels. Now, sometimes you have to do a little bit more algebraic manipulation, but you're going to get to a point where it's like, okay, I get a lot of cancellation. Let's look at what remains. There's a 10a times h, a 5h squared, and a 7 times h. Do they all have anything in common? They all have h. So we can pull that part out. That's the limit as h goes to 0 of h times 10 times a plus 5 times h plus 7 all over h. And now we can cancel off our h's. See, this is a beautiful thing. We're trying to get to the point where we can actually do a limit. Initially, when we do a limit, if we don't do anything, we're going to get 0 over 0. That's guaranteed. So you've got to find a way to cancel. And in particular, we know that the h downstairs is causing a problem. So we want to get a place where there's an h upstairs. And now we'd have that. The h's cancel. So our limit becomes just 10a plus 5h plus 7. So how do we finish by taking this limit? What do we do? Yeah, we can just plug in. Now, what do we plug in for? Yeah, we plug in h, because this is one of those times where it's like, wait, which one is, because there's two things. There's like a and there's h. So you have to think about which one is the one that you use. And the answer is, what's the limit telling you to do? Follow the limit. The limit says h goes to 0, so you put in h equals 0. So we end up with 10 times a plus 7. And that's the answer. So if you give me any a at all, lo and behold, I can tell you what the slope of the tangent line is at that particular point. 10a plus 7. Now, for those of you who have seen this before, you're like, that's a really long way to get to the answer. And yes, we're going to get to the point where you can do this in your sleep. Let's make an observation here. Did this plus 2 end up actually mattering? No. Now, can we think about a good reason why plus 2 wouldn't matter? So, if you think about the plus 2, if we were to graph our function here, the plus 2 shifts it up. But if I have a slope of my tangent line and I shift it up, what happens to the slope of the tangent line? Yeah, it doesn't change, right? It remains the same. So somehow, there are things where it's like, oh, this won't affect the derivative. And one of them is adding a constant. All right. Well, let's do another example. So suppose I have f of x equals absolute value of x. Here's a question. What is f prime of 0? Well, let's see if we can figure this out. So according to the rule, f prime of 0, that's equal to the limit, as h goes to 0, of f of 0 plus h minus f of 0 all over h. I'm just putting in the definition so far. Now 0 plus h is another way to say this, just simply h. And the f of h would be absolute value of h. The absolute value of 0 is 0. So I get the limit as h goes to 0 of absolute value of h over h. Now that limit is not so obvious right away what it is. So let's try to think about it in two sides. So suppose I break it up into the left and the right. Let's start from the right. In other words, I'm a little bit above 0. What happens to absolute value of h if I'm a little bit above 0? It's the same thing as just h. If I'm above 0, the absolute value doesn't have to do anything. So it'd be h over h if I'm above 0, also known as 1. What's the limit of 1? It's 1. If I'm a little bit below 0, what does the absolute value do? So someone says it's going to be opposite, right? Because, if I'm a little bit below 0, my input is a negative thing, but I have to come out with a positive thing. So I better put a negative. So it's negative h over h. Well, negative h over h, that becomes, oops, that's below, that's negative 1. What's the limit of negative 1? Negative 1. Now, we seem to have a challenge here. From the right, it looks like our answer should be positive 1. From the left, our answer looks like it should be negative 1. So what should we do? Should we say split the difference and say life is good? No, we don't do that. What do we do? Doesn't exist. Yeah. So what is the derivative of 0? The answer is it does not exist because the limit doesn't exist. See, the derivative is built off a limit. And so the limit tells us it doesn't exist. Now let's think about this in terms of our sort of intuition about what's going on with limits. Now when I say our intuition, remember what did we do? We said sketch your function. So we know how to sketch absolute value of x. And now zoom in. Okay, so if you zoom in, what are you going to see? You're going to see something that looks like that. So what do? Zoom in some more. What's going to happen? You're going to see something that looks like that. And what do? Keep zooming. But the thing is, no matter how much you zoom, what's going to happen at 0? You're always going to see that V shape coming in. Now when we talk about derivatives, we're saying, hey, that derivative is talking to us about that line. That line that we would see when we zoom in. But what happens is at this point, at 0, there's no line that you see. You never can zoom in far enough so it becomes flat. It'll always have that sharp turn. And therefore, there is no derivative. Because there's no tangent line. It doesn't become flat. So that's okay. It happens. It happens. Now, some side notes here. The tangent line, that part that you see when you zoom in, it's really important to get the following idea. It's what the function looks like. And so a nice way to think about what the tangent line is it's the best line. And the best in the following sense. It's the line which is best mimicking the function. So that is, again, the intuition. You keep zooming in, and after you keep zooming in close enough, what you see is flat. And so that line is that flat thing. It's the best approximation. So we have a couple things to know. Of course, we know the point on the line. We know the slope of the line. But we'll get to the point. This is foreshadowing of what's to come. Okay. So let me sidetrack here. So common ways to write the tangent line. So if you know your point, y minus your y coordinate is m, your slope, times x minus your x coordinate. And you can rewrite this by adding f of a to both sides to get y equals f of a plus f prime of a times x minus a. And you can also rewrite this in sort of slope-intercept form. y equals f prime of a times x plus f of a minus a f prime of a. But the moral here, that punchline, I just want to point out, is when we talk about saying that our tangent line is a good approximation, see this y right now is a tangent line, so we're going to come back and say, hey, f of x is about the tangent line when I'm near a. Because the tangent line mimics the function, and therefore that tangent line says that f of x is about the function at a plus f prime of a times x minus a. So this is going to be a really important idea as we go into the next part of the course. This is part 2 of the course. So let's see what we can do. Suppose we're told the following. Given that y equals 3x minus 7 is tangent to y equals f of x at x equals 4, what can we say about the function at 4? In particular, what is the value of the function at 4, and what is the value of the derivative at 4? So which one of these is easy to find? Okay. The derivative might actually be the faster one to find, because what does the derivative correspond to in terms of the line? The derivative corresponds to the slope. Can we read off the slope? Yeah, we can read it off. It's right there. It's 3. So f prime of 4, that's your slope, and therefore that's equal to 3. How do you find the function at 4? Is the answer negative 7? The answer is not negative 7, because negative 7, that's where you hit the y-axis. But you may not be looking at the tangent line when you want to look at where you hit the y-axis. All right, so how do you find f of 4? The answer is you plug 4 in. Because what's happening? You see, the tangent line mimics the function. So that means that the tangent line has to match the function. So if you think about this 3x minus 7, this is a function, and it's saying that at x equals 4, this new function, 3x minus 7, has to match the function f of x. So they're going to have the same value, so you plug 4 in. 3 times 4 minus 7. And what does that give us? It gives us 5. And that's our answer. So to find our derivative, read off the slope. To find the value of the function, evaluate. And so they're both fairly easy. So there's a very convenient way for us. If we have our tangent line, we can reconstruct information about our function. And then if we have information about the function, we can get our tangent line. So some of the problems that you'll see on maybe a quiz or possibly an exam will be like, oh, here's the tangent line, find this other tangent line. What's actually happening is it's saying, here's the tangent line, translate that information into what's the value of the function, what's the value of the derivative, get that to find new information about a different value of a function in a different derivative, and then translate that back into a tangent line. So be comfortable going back and forth from tangent line to data, data to tangent line. All right. Find the tangent line to y equals sine of 4x at x equals 0. Well, let's see. What do we need? Well, we need to know the value of the function at 0. So let's do that. So this sine of 4x, this is our f of x. So what can we say about f of 0? F of 0, that's sine of 4 times 0, which is 0, and sine of 0 is 0. And now we say, great news. We're passing through the point 0, 0. That's the point on our tangent line. What's the next thing we need? We need slope. Okay, so slope means I need f prime of 0. So according to the rule, that's the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h, using our definition. So f of h, well, that would be sine of 4h. F of 0, we already saw that was 0, all divided by h. Now this is good because we say, oh, wait a second, this kind of reminds us of something. Do you remember what this reminds? What does this remind us of? Sine of blah over blah. Wow, someone even remembers the technical terms. Right, good. So if you have sine of blah over blah, now the trick is they have to match. So we don't match yet. You have a 4h, but that's just an h. We needed to get a 4 there. Okay, I'll put a 4 there. Am I allowed to just do that? No. I got to compensate. Where else? What else do I need to do? Yeah, multiply by 4. I can put a 4. I'll put it over here just because there's more space. Just, I modified it. So first off, the modification doesn't change the value. I'm just modifying the way I'm expressing it. But I'm putting it so that the inside of the sign matches what's below the sign. Now we're of the right form. So this sine of 4h over 4h, what happens to that? That part goes to 1. And the 4, what happens to that? It's going to go to 4, because in fact it was always 4. Okay, so now we have the derivative. Are we done? No, we're not done, because we always remember the question asks us for something. We make sure we get what it's asked. It asks for the tangent line. So now what do we have? We have the slope. And we have the point. So y minus the y-coordinate is equal to the slope coming from the derivative, x minus the x-coordinate. And that simplifies to y equals 4 times x. And there you go. All right. Let's try another one. Find the tangent line to y equals 1 over the square root of x at x equals 4. All right, well, this should be fun. So first off, let's talk about the point. How did we get the point? Yeah, we already have the x-coordinate. So for the y-coordinate, we plug it in. 1 over the square root of 4 is also known as 1 over 2, or a half. All right, what's next? All right, we need to find the derivative to help us find the slope. So, the derivative at 4. So we're going to have f prime at 4. That's going to be the limit as h goes to 0 of f of 4 plus h minus f of 4 all over h. So this is the limit as h goes to 0. F of 4 plus h. Well, what will f of 4 plus h look like? 1 over the square root of 4 plus h, inside the square root. So think of the 4 plus h as just one thing, So everywhere where there was an x before, boom, it's a 4 plus h. Minus f of 4. Well, we actually computed f of 4. That's a half. And that's all over h. Okay, that's a big fraction there. All right, we're still getting 0 over 0, which means that we have to do more work. But what's the more work we should be doing here? What's our next step? So there's a couple things that you can do. And when I say there's a couple things, there's sort of two different orders. One thing you can do is you can actually do a conjugate here. You can say, hey, I'll multiply by 1 over square root of 4 plus h plus 1 over 2. And that will help get you closer. You get rid of that square root. Before I would do that, though, I would say, I see here fractions within fractions. And that's tough. Even just a single fraction is tough. But when I see fractions within fractions, it unsettles me. I'm not comfortable with that. So I want to get rid of the idea of fractions within fractions. So what can I do to help me get rid of that situation? Yeah, common denominator upstairs, add those two things together. So we're going to get the limit as h goes to 0. Here the common denominator would be if you multiplied the two of them together. So you'd end up with needing to multiply the first term by 2 and the second term by square root of 4 plus h. Then your common denominator would be the square root of 4 plus h times 2. And that's all over h. Now here's the nice thing is you can think of this all over h as being the same as 1 over h multiplied there. So now you don't have a fraction within a fraction. And now we say, okay, what's our problem? Well, downstairs we still have that h. We want to cancel it. Upstairs you have that 2 minus square root of 4 plus h. Now what do you do? Well, any idea? Conjugate. See, the conjugate is a useful tool because it's going to help us get a square. If we square a square root, that's going to help get us closer to the truth. So, applying that, we're going to get the limit as h goes to 0. Upstairs, we get 2 minus square root of 4 plus h and 2 plus square root of 4 plus h, which is going to become 4, 2 squared, minus, parenthesis, 4 plus h. Downstairs, well, we have a whole bunch of stuff. We have a square root of 4 plus h, a 2, an h, and a 2 plus square root of 4 plus h. All right, upstairs, we have something nice. What happens? The 4's cancel. So you're left with negative h. Now, this is great that we have a negative h on top because what does negative h have in common? Well, in fact, it's just one term. It has negative h. But what else do we see? There's an h on the bottom, h downstairs. So I can actually cancel this h with that h downstairs. So if we were to do that, it's kind of 2 steps we did, but we can handle that. We're left with negative 1 on the top over square root of 4 plus h times 2 plus square root of 4 plus h. Now, the important thing is that when we cancel those h's, we canceled something which was causing zeros on both top and bottom. So the next thing we should do after we've canceled something which was causing zeros is to do what? Plug it in. And maybe we're done. And in fact, not just maybe we're done, we know we're done. How do we know we're done before we even evaluate? Because we have negative 1 on the top. Negative 1 means it's game over, man. Game over. Whatever happens, it happens right now. Okay, so now you just have to evaluate the bottom. Square root of 4, 2, 2, 2, 2, still 2. Square root of 4, still 2. All right. So you get 2 times 2 times 2 plus 2, which gives us a grand total of 16. So minus 1 over 16. So that's our slope. So we're not done because, again, this was a find the tangent line question. But we're close because we have our slope and we have our point. And we put the two of them together. So we can, let's see if we can fit it in here. So y minus the y-coordinate, which is 1/2, is equal to our slope minus 1 over 16 times x minus the x-coordinate, which is 4. And unless we're told to simplify, that's our answer. We don't have to go any further. All right. So given the parabola, y equals, so does anyone have a favorite parabola? What? X squared, that's your favorite one? All right. I guess, we all start out with simple parabolas in life. Okay. And the line y equals, what? X. Find all tangent lines to the parabola which are parallel to the given line. Also find all tangent lines to the parabola which are perpendicular to the given line. Now, in the interest of time, and the fact that we've sort of have seen this type of argument before. So if this x squared, thinking this as our f of x, if we went through, if I ask you what is f prime of a, what would it turn out to be? It'd be 2a, yeah. Derivative of x squared is 2x. This will make more sense as we go on. But it's the same process. We've done a quadratic before. There's no real surprises. We want to get to the fun stuff. Okay, so our derivative at any particular point, we just double the value where we're at. Now, we're told to do two things. We're told to find, first off, find tangent lines which are parallel, and then we're going to do perpendicular. So when are two lines parallel? They have to have the same slope, right? Okay, that's fine. So, what's the slope of this line? 1. So for parallel, what we need is slope has to equal 1. So we take our slope of our tangent line, that's 2a, we set that equal to 1. What does that tell us about what a should be? A should be 1/2. So now we know where our tangent should occur. Our tangent line should be at a equals 1/2. Well, that's not really a point, that's really our x-coordinate. What's our y-coordinate? 1/4. Because our function is we square. So if our x-coordinate is 1/2, to get our y-coordinate, we square that, we get 1/4. And therefore, our line, which is parallel, y minus our y-coordinate is our slope, x minus our x-coordinate. And if you wanted to, you could clean that up. You could say y equals x minus 1/4. Because you can add 1/4 to both sides. Okay, so that's the parallel. There's a second part, perpendicular. When are two lines perpendicular? Yeah, so there's that sort of phrasing. Now, the moral here is that perpendicular means negative reciprocal. So, for example, if I have slope m, then I would flip it upside down and put a negative in front. So for our case, our original slope is 1. So if I want perpendicular, what should my slope be to achieve that? Negative 1. So we do the same process. So I need to have that 2 times a, that's my slope at my tangent line, has to equal negative 1. What should that tell me about a? Negative 1/2. So what's the point? Negative 1/2, comma, 1/4, because we squared. So y minus our y value is equal to the slope, negative 1, x minus our x value. And again, you can clean this up. You can say y should equal, this would be negative x, and let's see, this would be plus 1/2, but then you have a minus 1/2, so it's really minus 1/2 plus 1/4. So it's negative x minus 1/4. So they're usually not quite so nice and symmetrical, but somebody wanted some nice functions. That's all right. We'll save the interesting functions for the exam. All right. So, last problem. And you might notice, hey, there's a star on here. That means it's a good one. This is a good one. Find all lines which are tangent to both f of x equals 2x squared plus 4x plus 2, and g of x, which is negative x squared plus 2x minus 1. Now, we don't ask you to graph it, but we could graph this one. It's actually not too bad. Because if you look at what this function is, if you pull out a 2, x squared plus 2x plus 1, do you recognize x squared plus 2x plus 1? What is it? It's x plus 1 squared. Over here, you could pull out a negative, x squared minus 2x plus 1, and then what would you have? X minus 1. squared. So in terms of what you have, you can see, all right, I have one parabola that's been shifted over so that the vertex here is at -1, and then it's pulled up a little bit. So here's my 2 times x plus 1 squared. Then I have another parabola which has been shifted over here to +1, but it opens down. All right. And so our goal is to find all lines which are tangent to both curves. I claim that there's one easy answer, and then there's another answer which is going to take us about 10 minutes. Which is the easy answer? The x-axis. The line y equals 0 is tangent to both of them. Because you can see that for y equals 0, it touches both curves at a single point. It's not crossing them. All right. So at the end of the process, we should be able to recover y equals 0. And if we didn't get y equals 0, we'd be in trouble. Now, what's the subtlety about this? Well, the thing is that you can even see it here when you have y equals 0. The tangent places, the locations where you have a tangent line are not the same. All right. So this is going to make it interesting. So now we have to start thinking. How do we figure this out? Well, let's do the following. Let's say we're going to have our tangent line that we're after. Maybe we'll say it's intersecting here at A, and maybe it intersects at this one down here, it's B. This is obviously not the right ones because those lines are not the same. But all right, so I have a tangent line to the first function, it's going to hit at A. The tangent line for the second function is going to hit at B. Now, let's ask a really very simple sounding question. So be ready to give a simple answer. When are two lines the same? Slopes are the same. Intercepts are the same. That's an easy answer to an easy question. But we can use that. Okay, so here's the idea. Let's actually figure out, all right, so I have this function f of x. And what would be f prime at A? So you go through, take the derivative, what would you get? 4a and 4. If you did it for g prime at B, what would it be? Negative 2b, or is it not 2b? Well, it's negative, so it's probably the not 2b. And then plus 2. So that would be if you ran through the limit definition. After you do about 2 or 3 of these with quadratics, you're like, okay, you always see the same thing over and over. In the interest of time, we're going to skip that. So here's something that we have to have. We need to have that 4a plus 4 had better be equal to negative 2b plus 2. Or we can rearrange things. 4a plus 2b had better be equal to negative 2, or 2a plus b had better equal to negative 1. So there's one fact that we need. That's not enough. All right, so we said the slopes have to match. The other thing we said is that the intercepts have to match. And we wrote this down and sort of like didn't pay much attention to it, but we actually have a formula for the intercepts. So the slope is the derivative. The intercept, I'm going to copy it down here, that would be f of a minus a times f prime at a. Okay, that's our intercept. So for us, well, f of a, 2a squared plus 4a plus 2, subtract a times 4a plus 4. So, cleaning this up, that's 2a squared plus 4a plus 2 minus 4a squared plus, minus 4a, because the minus goes through. The 4a and the minus 4a cancel. So that makes 2a squared plus 2. That's the y-intercept for the tangent line here at A? Well, that's got to equal the y-intercept for the other tangent line at B. So we're going to run through it. Do the same thing. G of B minus b squared plus 2b minus 1 minus b times minus 2b plus 2. And that's minus b squared plus 2b minus 1 plus 2b squared minus 2b. The 2b's cancel, so this becomes b squared minus 1. So the conclusion is that we also need to have minus 2a squared plus 2 had better be equal to b squared minus 1. So there's our second equation. We now have two equations and two unknowns. So when you have two equations and two unknowns, what should we do? We should solve. How do we solve? Well, in this case, we can solve by substitution. So let's solve for b. I can say that b is minus 1 minus 2a. And now I can put that information in here. So minus 2a squared plus 2 is going to be equal to minus 1 minus 2a squared minus 1. All right. This is good. We're getting closer. Square that out. 1 cross terms will be plus 4a, and then plus 4a squared, and then minus 1. And now we say, okay, cool, move everything to one side. We're going to get 6a squared, because there's 4a squared plus 2a squared, 6a squared. Then we get plus 4a, and then we get minus 2 equals 0. Which we could also say 3a squared plus 2a minus 1 equals 0. Now, if the problem were nice, what should be true? It should factor. Do you think the problem is going to be nice? What? You're supposed to say, of course it is, because our instructor loves us. In fact, it has to be nice. In fact, we know a factor without even working. Can you see what one of the factors has to be? Do you see this right here? That's a tangent line that works. Where's the tangent at? At negative 1. So it better factor as a plus 1, because a equals negative 1 has to be a solution. And then there should be something else. So what's the something else? 3a minus 1. Now, you can go back and check. 3a squared minus a plus 3a, that's 2a and minus 1. So, after all that, we get to the following thrilling point. We have that the tangent line will happen at a equals negative 1, or at a equals 1/3. Now, we actually already know the tangent line for a equals negative 1, so that one was the one we already said before we began. So this is going to produce the line y equals 0. So now we say, aha, there's one more line. One more line which is tangent to both. So at a equals 1/3, what's going to be the slope of that line? Well, plug in a third. 4/3 plus 4, also known as 16/3. That's our slope. And what else do we know? Well, what's the point? Well, we can take it and say the x-coordinate is 1/3. The y-coordinate would be 2/9, because 2 times the third squared, plus 4/3 plus 2, which, of course, that's 1/3. We can think of this as 2/9 plus 12/9 plus 18/9, which is 32/9. And therefore, bring this all together. Okay, I need a bigger piece of paper. All right, y minus the y-coordinate is equal to the slope, 16/3, x minus the x-coordinate, 1/3. And there's that line. You wouldn't have guessed that. But we didn't have to guess it, because we've got math. And that's far better than guessing. All right. Done. Done for today.